So far in this unit, we've been looking at properties related to individual molecules, how their collision forces lead to pressure and ultimately to the ideal gas law, how um, there's a distribution of speeds given by the Maxwell-Boltzmann function, and how there's an equal amount of energy in each degree of freedom. Each, say, kinetic energy x, y, and z has an equal amount of energy. That's known as the equipartition theorem. So while we're dealing with the individual behavior of molecules, we're just going to continue with the discussion of microstates, macrostates, and ultimately lead into some key facts on statistical mechanics. So we have introduced these words before. The macrostate, you'll recall, is the large-scale state of the system defined by properties like temperature, entropy, internal energy, etc. The microstate is the precise specification of all the atoms and molecules in that sample in terms of where they are and what their velocity is. Degeneracy is a term that refers to the fact that a number of microstates will give exactly the same macrostate, and the degeneracy is that number. It's the number of microstates that give you equivalent macrostate. As an example, let's say we have a magnetic system of n atoms, and the macrostate of no net magnetization, so that's going to be half of the atoms, so we have an upwards magnetization, and the other half of the atoms will have a downwards magnetization. So there's no net magnetization. Now there's a number of microstates that correspond to this macrostate. So for instance, it could be, up, 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 down, 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 right? So all up here, dot, 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 all down here. Or you could have down, 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 and then up, 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 up. Or you could have up, down, etc. And so all of those are equivalent or degenerate microstates. So these are degenerate microstates because they all give the same macrostate, this macrostate here. Now the main assumption of statistical mechanics is that all microstates are equally likely. As a result, for our system, where there are, if there's n atoms, each atom has two possibilities, up or down, so there's 2 to the n total outcomes. Then for a given microstate, the probability is 1 over 2 to the n. But for the macrostate, if we define omega as being the degeneracy, then for a particular macrostate, the probability becomes omega over 2 to the n, because omega is the multiplicity or the number of degenerate microstates, and n is the number of atoms. So we see that the macrostates that have the highest degeneracy, i.e. the greatest number of possible internal rearrangements that give the same overall macroscopic state, those will be the most likely ones, as we've seen before. So that's largely a review. So we want to calculate the degeneracy of this magnetic atom system. Let's start with a mathematical analogy, the binomial theorem. So let's expand x plus y to the power of 14. Now there's 14 brackets here, and each bracket has 2 terms, so there's 2 to the 14 terms in this expansion. That's quite a few. And so the first one is going to be x to the 14, y to the 0. And then there's going to be, the next one will be x to the 13, y to the 1. There's only one way to get this x to the 14 term. You just pick the x out of each bracket. But to get x to the 13, it turns out there's actually 14 ways to do that. Because you've got to pick one y. Well, you could pick it out of the first bracket, the second bracket, etc., etc., etc. You could pick it in 14 ways. Now, at the other end of this expansion, there will also be 14 ways to get x to the 1, y to the 13, and there will be only one way to get x to the 0, y to the 14. Now, these coefficients, you may recall, are given by combinatorics. So this is 14 brackets. I'm choosing 0 y's. This is 14 brackets. I'm choosing 1 y, etc. So I can write this binomial expansion as a sum over I from 0 to 14 of 14 choose I, and it's going to be y to the I x to the power of 14 minus I. So that's just the binomial expansion. Now, why are we talking about this? Well, an example macrostate would be one of these terms. So perhaps like x to the 11, y to the 3. And in our expansion, that x to the 11, y to 3 is going to come up in a number of different ways. For instance, it could be x, that's 11 x's and then 3 y's. Or it could be x, that's 10 x's and then y, and then x. So you could pick the x out of the first 10 brackets, then pick 3 y's, and then pick the last x. Or you could pick x out of the first 11 brackets, and then the remainder 3 y's. So these are both terms that are going to come up. They're going to be equivalent to this x to the 11y to the third macrostate. So what is the degeneracy of that macrostate? Well, it's given by this combinatoric coefficient. It's 14 choose 3. And we know that's given by 14 factorial over 14 minus 3 factorial times 3 factorial. And so working that out, that's 14 times 13 times 12 times 11 factorial. That cancels the 11 factorial here. And then we have 3 factorial, which is 3 times 2. That's 6. That cancels out the 2. So we end up with 2 times 13 times 14. So that's 26 times 14. That is 364. So the probability, the quote-unquote probability of getting x to the 11y cubed is the number of degenerate microstates. And again, there's 364 terms in this expansion that are going to have x to the 11y cubed over the total number of terms, which is 2 to the n. So 364 out of the 2 to the 14. So 364 of these terms in this huge expansion. But of course, there'll be 16,384 terms in the expansion. Wouldn't want to do this by hand. So 364 of them will contribute to this x to the 11y cubed term. All right, so why are we doing this? Well, because, of course, it's a perfect analogy for the magnetic atom problem, because with magnetic atoms, they can be up or down, so we could think of like up as being the x and down as being the y. So if we only had 3 atoms, let's not do 14, let's just do 3, then the first one could be up or down, the second one could be up or down, the third one could be up or down. Now this is small enough just to expand directly, right? It could be up, 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 and then we can have 2 ups and a down, and up to 2 downs, and 3 downs. But there's 3 ways to get 2 ups and a down, and there's also 3 ways to get 2 downs and an up. So for our macro states then, we've got 3 up, 2 up, 1 down, 1 up, 2 down, and 3 down. And the multiplicity we can see is 1, 3, 3, 1. That's exactly what you would get from your combinatorics, right? So this is going to be 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. And for the probability, we would say that you see there's 8 possible outcomes there. So this is 1/8, 3/8, 3/8, and 1/8, because there's 2 to the 3 is 8 total possible states or outcomes. So if we make a graph then of the probability distribution function, PDF, just to show how likely these various states are, 3 up, 2 up, 1 up, and 0 up. So this is like 1 part in 8 and 3 part in 8. So it's a symmetric function. It looks like that. And Of course, we're not so much interested in in 3 atoms as we are in n atoms. So what happens to this analysis that we've done here and this distribution function if n gets really big? Well, it's still going to be combinatoric coefficients that give us the quote-unquote multiplicities or degeneracies. So it's still going to be n choose k, but as n gets really, really big, say like a mole, well, you can't do the factorial of a mole, right? Your calculator can only do, I don't remember what it is, but maybe up to like 20 factorial or something like that, and then it just runs out of powers of 10. So we need an approximation for n factorial, and we're going to develop it here. It's known as the Stirling Approximation. So here's the definition of n factorial. You just multiply starting at n by successive smaller numbers all the way down to 1. So if we were to, say, take the log of both sides, the natural log, then the log of a product is the sum of the logs, so we could write it like this. Oh, right. And then in summation notation, that's the sum of ln k, and k is going from 1 up to n. But as n gets very large, then these steps of 1 proportionally get quite small, and we've essentially got a Riemann sum here. It's a Riemann sum, so notice this is approximate. The Riemann sum that we could use to evaluate the integral of ln x dx from 1 up to n. Now, this you can integrate by parts, right? Call this part, let's see, the u, and then call this the dv. And it integrates to be x ln x minus x between 1 and n. So that's n ln n minus n. And putting in 1, you get 1 times log 1, which is 0, minus 1. So it's minus 1, it's plus 1. But with n being, say, a mole, the 1 is just basically tiny. We can ignore that. So we've got an expression for the log of n factorial. But of course, n is the same as n ln e, because ln of e is 1. So if this is the ln of n factorial, then we can put those things together. This is going to be the ln of n over e to the power of n, which tells us that n factorial is approximately this, n divided by e to the power of n. Now that's what I'll call the simple Stirling approximation. A better version of that, which involves a few more steps in the derivation, you get an extra factor of 2 root 2 pi n in front. And we're going to use this now to look at the probability distribution function for, say, n spins, or n atoms rather, where n is a big number. So what if we were to do that then and say, okay, so what's the multiplicity of the up equals down, the most common state? So if we've got n atoms, that means there's going to be n over 2 up and n over 2 down. What would that look like? Well, we know that's going to be n atoms choose n over 2 up, so that's n factorial over n minus n over 2 times n over 2 factorial, which is this expression here. So what are we going to do with that? Well, you can't go plugging that into your calculator. Even if that's 100, it's not going to work. So we're going to have to approximate. So we approximate the numerator using the Stirling approximation. And then we approximate the denominator. Now, when we do the denominator, we're going to get the same thing twice. So it'd be root 2 pi n over 2 from this one. And then again, and I'll just bring those together right off the bat. And then the other thing that you're going to get is n over 2 over e all to the n over 2, and then n over 2 over e all to the n over 2. Because remember, u factorial was root 2 pi u, and then it's u over e all to the u. So I just put n over 2 into there. So that's why it's n over 2 to the power of n over 2. All right, so we can do some simplification here. You're just squaring this bracket, so that ends up being 2 pi n over 2, and then the 2's cancel. So I didn't do anything with the numerator, but I multiplied those two things together. And then we could take one more step, so we see that we've got root 2 pi n over pi n. That works out to be root of 2 over pi n. And now, let's next focus on the e term. So you're going to 1 over e to the n in the numerator. And then I'll pull out the e's from each of those brackets, which I can do by the exponent laws. And we see that this is just going to add to give 1 over e to the n, and that'll then cancel with the 1 over e to the n in the numerator. So this looks horrible, but it actually isn't that bad. Then let's focus on the n term. So we're going to have n to the n here in the numerator. Then we've got n over 2 to the n over 2, and n over 2 to the n over 2. So this works out to be n over 2 to the n, which is n to the n over 2 to the n. So once again, the n to the n cancels, and I get this for the multiplicity of the spins up equals spins down state. And then, of course, the probability of that seems pretty small, right? So it would be this over 2 to the n, because that's the number of possible outcomes. That's root of 2 over pi n. Now remember, n was around a mole, so this is an extremely small number. So it looks tiny, but it turns out that it isn't, because the width of the curve is about root n as well. So when you multiply those two together, you get an overall probability of about 1. So how can we get to that easily? Well, it turns out that this binomial two-outcome probability distribution is very well approximated by a normal curve. Now, we did the probability of a 3-atom system. Here is just a graphic showing you that for a 6-atom probability distribution function, how closely it is matched by the normal bell curve. So as n gets bigger, that approximation is, or rather that agreement's even better. So what is a normal curve? Well, if you've studied statistics, you're familiar with this expression for the normal curve. So it's a decaying exponential. It peaks at a value mu, which is called the mean. Now, for our spin system, mu will just be n over 2, because n over 2 is the most likely outcome. It's where the probability is highest. Sigma measures the width of the curve, and you can see here between mu plus sigma and mu minus sigma, 68% of your probability, i.e., your most likely outcomes are found within 1 sigma of the mean. Now, for our binomial system, say for the magnetic atom, where it can only have 2 outcomes, the width can be shown to be root n over 2. And that's going to have some interesting implications for us. And so n in this, we're dealing with, say, the probability of outcome n, where n is the number of, say, up spins. It's the number of up spins. So, for instance, if we put in n is the mean, is n over 2, then we get a 0 in the exponent. And so you get 0 minus 0. Putting in sigma, the standard deviation, doesn't change anything. That's still e to the 0, so that's all 1. And then putting in sigma squared down here, you get n over 4. So that is the root of 2 pi n all over 2. And then we could bring the 2 up here. And that simplifies, of course, to the root of 2 over pi n, which is exactly what we found before as being the probability of that n over 2 state. So if we, say, had 100 atoms, then this is going to be 2 over 100 pi square rooted. That's not a very big number, but it is still the most likely outcome. Okay, so with 100 atoms, this would be 50. And we know this distribution is going to be is going to be peaked at that point, the most likely up equals down macrostate. With 100 atoms, we get 10 over 2 is 5 as being our width. So most of our probability is going to be 5 less or 5 greater. And so here will be our probability distribution. The probability is going to drop off very quickly once we're outside this range. So these will be our most likely outcomes. Other macrostates out here are very unlikely. So the most likely state for the spin system is one that's very close to up equals down. And why is it the most likely? Well, because it has the highest degeneracy or multiplicity. Now, there's no force that pushes the system towards that state. It's just the laws of probability. Because there's the highest number of equally likely microstates in that macrostate, that's why the system tends to end up there. Now, we saw in this derivation that omega, the degeneracy, is a huge number, so it makes sense to introduce a logarithmic scale. And we'll define a new function s that's proportional to the logarithm of the degeneracy. This is the Boltzmann constant k. Because omega, the degeneracy, has no units, our s function is going to end up having the same units as the Boltzmann constant, i.e. joules per Kelvin. Now, as a natural log of the degeneracy omega, s increases in proportion to omega, which means that given that the most likely state is the state with the highest omega, it's also the state with the highest s. So s is likely to reach its largest value when the system is at equilibrium. We'll say more about this s function in our next class.